Hi, welcome to Hardware Basics. Today we will discuss about power supply decoupling. Imagine powering up your PCB after weeks of work and it only works sometimes. One moment the microcontroller is running fine. The next moment it resets. LED starts flickering. Sensor report nonsense values like 100 degrees Celsius in 25 degrees Celsius room. And there is no smoke, no burning smell, just chaos. Here is the twist. The problem might be single tiny component. A capacitor you either misplaced or forget entirely. And in the next few minutes, I am going to show you how this tiny thing can kill your PCB and how to stop it from ever happening again. Stay with me because the most important part in the second story. Power supply decoupling. Decoupling sound complicated, but here is the truth. Every IC, your microcontroller, FPGA, op-amp, sensor, switching millions of states every second. And every switch demands a tiny burst of current in nanoseconds. Your power supply cannot react that fast. Your traces cannot deliver current that fast. Your voltage cannot stay stable under that load. It results in microcontrollers reset randomly, sensor output, garbage value, buses glitch, entire products fail in the field, all because of microscopic voltage dip that you never see unless you know where to look. Decoupling capacitors are miniature power banks. They sit right next to every IC pin, ready to deliver energy instantly when IC needs it. Let me tell you a real story. There was a startup building an IoT device. The design was perfect, schematic perfect, firmware perfect. But every time Wi-Fi module transmitted, the microcontroller reset. Every single time. Swap the firmware, replace the memory chip, reroute the signal, replace the microcontroller. Nothing gonna work. Then someone noticed it. The zero point 0.1 microfarad capacitor that was supposed to sit right beside the Wi-Fi chip was missing. We placed the capacitor power on the board. Everyone held their breaths. No reset, no glitch, nothing. Just silence. The board finally worked. Not magic, not firmware, not luck. Decoupling. When an IC draws sudden current, your PCB trays behave like a long, thin garden hose. Try pulling the water instantly through a long hose, the pressure drops. Same thing happens electrically. Your voltage dips for a few nanoseconds. That tiny dip is enough to crash your microcontroller. A decoupling capacitor is just like a water tank placed right beside your IC, instantly deliver energy, instantly stabilize it. Without it, you are sending your board into battle without armor. You can't just throw capacitors anywhere and hope for magic. Placement is everything. Here is the rule. The capacitor must be physically close to the IC power pin as possible. If the trace is long, the capacitor becomes useless. Use different values of capacitor. For example, zero point 0.1 microfarad capacitor for high frequency spikes and 10 microfarad for low voltage dips. Here are something nobody tells beginners. Your PCB trace length is more important than capacitor value. A A perfect capacitor placed 3 cm away is worse than a small capacitor placed 3 mm away. Now for the second story I mentioned earlier. We had an audio amplifier project. Simulation perfect, design perfect. But in real life, the audio hissed, crackled, little spikes riding on the voltage rail. We replaced the op-amp, replaced resistor, tried different power supply, still noise. Then we try something simple. We placed a 0.01 microfarad and zero point 0.1 microfarad capacitor right to the op-amp power pin. Instantly, the audio became crystal clear. The entire problem was noise in the power line. Decoupling killed it instantly. Here are the top beginner mistakes. Number 1, not placing capacitor at all. Number 2, placing capacitor too far from the IC. Number 3, using only one capacitor value. Number 4, trusting the power supply too much. Number 5, using long routing that increase inductance. Every one of these mistakes can cost you hours, days, or even weeks of your work. Here are some simple rules to solve these problems. Place every capacitor as close as possible to IC power supply pin. Use different values of capacitor for different frequency spikes. Keep trace short and wide. Use ground planes. Don't chain capacitor in series. If you doubt, measure it with oscilloscope. If you follow this checklist, you can avoid 90% of power stability bugs. Almost every PCB engineer learns this lesson the hard way. Even Apple has full team dedicated to power supply integrity. If you get this wrong, you lose sleep, you lose time, you lose confidence, you lose clients. And you if get it right, your board work first try, debugging disappear, you become the engineer everyone trusts. So next time you design a PCB, don't underestimate the tiny capacitor sitting quietly beside your ICs. They are silent guardian of your design. One missing capacitor and your entire board can fail in worst possible way. If you want to avoid next PCB horror story, subscribe to our channel because in the next video I am going to show you exact capacitor placement that kills board with real example from real failed product.